So today we're tackling a concept that really twists our classical intuitions into knots. Particle spin.
Oh, yeah, spin.
When you first hear spin, you probably picture a tiny planet or maybe a spinning top, right?
That's the usual image, yeah. It comes from the early days, pioneers like Uhlenbeck and Goudsmit back in 1925.
And that picture, it sort of suggests spin is angular momentum.
It does. And if it were like a tiny spinning top, it should also be a store of rotational kinetic energy, like a flywheel.
Exactly. You could, in theory, spin it faster, store energy, slow it down, release it. Simple mechanics.
But, and this is the big but.
Here's where it gets really interesting, isn't it? What if that intuitive analogy, while, historically important, is just fundamentally misleading?
That's precisely the issue.
What if this thing called spin, which, mathematically is described as angular momentum, and it's definitely associated with energy, what if it actually cannot function as a variable energy store?
That's the paradox we need to unpack.
Right. That seems like the core problem we're exploring today for you.
Exactly. And what's so fascinating is this isn't just some academic puzzle. No way. Resolving this paradox, it forces a huge shift away from our everyday thinking. And, it's actually the foundation for some really advanced tech we use now.
Okay, so what's the plan?
Well, we'll walk you through why spin is purely quantum mechanical, why it's an intrinsic, unchangeable property.
Like its charge or mass?
Precisely, and we'll show how its energy comes purely from interaction, not some internal spinning motion.
So our mission today, dismantle that spinning top idea.
And replace it with the quantum reality, which honestly is even more mind-bending.
All right, let's get into it. That classical energy reservoir idea. Where does it first start to break down? What's the most crucial point?
I'd say the absolute most crucial concept is that spin is intrinsic. It's fundamental to what a particle is.
Okay.
Think about an electron. It is a spin-12 particle. That's its nature. It hasn't been, spun up.
So you can't,
to
take the spin away from an electron.
No more than you can take away its charge. It's inherent. That's why we often prefer the term intrinsic angular momentum. It gets away from the spinning idea.
Oh, okay. So it's not acquired like the rotation of a flywheel.
Exactly. A flywheel spin is extrinsic. Particle spin is intrinsic. Big difference.
That's a huge conceptual shift. But that mental image of spinning is persistent. So what are the hard facts, the experiments, or paradoxes that really kill the classical rotation model?
Oh, there are several showstoppers. First, the faster-than-light problem.
Right, I've heard of this one.
If an electron were a tiny spinning ball, given how small we know it is basically point-like and its measured magnetic strength, then its surface would have to be spinning way, way faster than the speed of light.
Which violates relativity. Instantly problematic.
Totally. And building on that, there's the point-particle issue itself.
If it has no size.
Exactly. How can a mathematical point rotate around an axis? The concept just doesn't make sense for a point.
So the spin isn't rotation of the particle itself.
It's a property of the quantum field excitation that we perceive as the particle, not a physical spinning object.
Okay. That's already pretty weird. Is there more?
Oh, yes. Perhaps the weirdest part. The 720-degree rotation. A normal object, you rotate it 360 degrees, it looks the same again.
Makes sense.
A spin-12 particle, like an electron, you have to rotate its quantum state 720 degrees, 2 full turns, for it to return to its original state.
Wait, 2 full turns? What happens after one turn, 360 degrees?
Its wave function flips its sign, it gets multiplied by -1, mathematically different even if some properties look the same initially.
That's deeply strange.
Yeah.
And this isn't just theory.
Nope. Verified experimentally. Neutron interferometry experiments have shown this directly. Clear proof spin isn't just 3D rotation.
No classical analog at all.
None whatsoever. And this weirdness leads straight to another key point. Spin is quantized.
Meaning it comes in fixed amounts.
Exactly. Both its total magnitude, the spin quantum number, and its projection on an axis ohms are restricted to specific discrete values.
For an electron, that's S equals 12.
Right, and its projection can only be +12 or -12. Spin up or spin down. That's it.
No in-between values.
Nope. Just those two options along any given axis. This discreteness is totally incompatible with a classical energy store, which could hold any amount of energy continuously.
Okay, so we have the speed limit violation, the point-particle problem, the 720-degree rotation, quantization. Is there a final nail in the coffin for the energy reservoir idea?
I'd say it's the immutability of the spin magnitude.
Meaning?
While the orientation can change a spin flip, The fundamental amount of spin, that S equals 12 for an electron, can never be changed.
So there's no spin speed control knob.
Precisely. You can't speed it up or slow it down, and if you can't change its speed, it simply cannot work like a flywheel, storing variable amounts of kinetic energy.
Okay, the spinning top analogy is officially dismantled. So
Yeah.
if spin isn't storing kinetic energy, where does the energy we do associate with spin actually come from? That's a critical question.
It is. And the crucial link here is the spin magnetic moment.
Ah, the magnetic connection.
Right. Any charged particle with spin automatically, intrinsically, has a magnetic dipole moment, like a tiny compass needle,
And this is tied to the spin.
directly proportional to the spin angular momentum. For an electron, there's something called the G factor, which is very close to 2, relating the magnetic moment strength to the spin. It acts like a tiny bar magnet locked to its spin axis.
Does this apply only to charged particles? What about neutrons?
Good question. Even neutral particles like the neutron have a magnetic moment. It's because they're made of charged quarks, and their spins and charges combine to create a net magnetic moment.
Okay, so this intrinsic magnetic moment is the key.
It's the key. Spin itself doesn't contain energy, but it gives the particle a magnetic handle.
A way to interact.
Exactly. The energy connected to spin is potential energy of interaction. It only shows up when the particle and its magnetic moment are in a magnetic field.
So no magnetic field, no spin energy.
In this context, yes. The potential energy arises from the system of the particle in the field.
I think the clearest example of this is the Zeeman effect, isn't it?
Absolutely perfect example. You put an atom in an external magnetic field.
And its spectral lines split.
Right. That splitting happens because the electron's spin magnetic moment interacts with the external field. The spin up and spin down states, which had the same energy before.
Now have different energies.
Correct. The state aligned with the field gets lower potential energy. The anti-aligned state gets higher potential energy.
And that energy difference is clearly potential energy of the particle in the field. It's not internal kinetic energy.
Precisely. Turn off the field, the splitting disappears, the energy difference vanishes. It's all about the interaction.
Does this connect to other things we see in atoms?
It does. Think about spin-orbit coupling. That's an internal interaction between the electron's spin and its own orbital motion around the nucleus, which creates its own magnetic field.
And that also causes energy level splittings.
Yes, it's responsible for the fine structure in atomic spectra, like the famous yellow sodium D line. It's not one line, it's actually two very close lines, a doublet, because of spin-orbit coupling.
So again, it's interaction energy causing the effect.
Consistently, all spin energy is interaction energy.
Okay, let's really crystallize this contrast for you, the listener.
Yeah.
Classical flywheel versus particle spin.
Go for it.
Source of energy, flywheel kinetic energy of rotation. Spin, potential energy of interaction with a magnetic field.
Nature of spinning, flywheel, actual physical rotation, spin an intrinsic quantum property, definitely not physical rotation.
Energy variability. Flywheel continuous depends on speed. Spin discrete depends only on orientation in a field because magnitude is fixed.
Right. Speed matters for the flywheel, only orientation matters for spin energy.
Governing principles. Classical mechanics for the flywheel.
Quantum mechanics for spin. Fundamentally different frameworks.
And example systems.
Yeah.
A big mechanical flywheel stabilizing power.
Versus a single electron spin being manipulated in an MRI machine. Totally different scales and concepts.
Okay, that contrast makes it very clear. But now, energy conservation. If spin isn't a classical reservoir, how is energy conserved when a particle's spin state changes, like in a spin flip?
Great question. A spin flip isn't a gradual slowing down or speeding up. It's a discrete quantum leap.
A jump.
An instantaneous jump between those allowed energy levels, spin up and spin down in the simplest case. For that jump to happen, the exact energy difference between the two states must be exchanged with something else.
Another system.
Yes. It's an all-or-nothing transaction. Energy has to be perfectly conserved, unlike a flywheel that can just gradually lose energy to friction.
So how does this energy exchange usually happen? You mentioned photons earlier.
Right, radiative transitions are very common. Photons are involved.
How does that work?
Well, if a particle flips from a higher energy spin state to a lower one, it can emit a photon. And the energy of that photon exactly matches the energy gap between the spin states.
Is there a famous example of this?
The most famous is probably the 21-centimeter hydrogen line. Astronomers use it constantly.
What's happening there?
In a hydrogen atom, you have a proton and an electron, both with spin. When the electron flips its spin relative to the proton spin, going from a slightly higher energy state to a lower one, It emits a photon with a wavelength of 21 centimeters.
Wow. And the reverse, going to a higher state.
Needs to absorb a photon with precisely the right energy to make the jump. That's resonant absorption, the basis for spectroscopy. You shine light on atoms, and they only absorb the specific frequencies matching their energy level gaps.
And what about angular momentum in these photon exchanges? Is the spin itself changing magnitude?
No, remember, the spin magnitude is fixed. When a photon is absorbed or emitted, photons also carry angular momentum, that angular momentum is typically exchanged with the electron's orbital angular momentum, or the overall system, not its intrinsic spin amount. Conservation holds, but it's subtle.
Okay, so photons are one way. Are there others? You mentioned condensed matter earlier.
Yes, especially in solids or liquids, spin-lattice relaxation is really important.
Lattice. What does that mean here?
It just means the particles surrounding the atoms and molecules around it. The lattice is constantly vibrating due to thermal energy.
Like heat?
Essentially, yes. These thermal vibrations create tiny, fluctuating local magnetic fields.
Okay.
If a component of these fluctuating fields happens to oscillate at just the right frequency matching the spin-flip energy gap...
It can trigger the flip.
Exactly. It can induce a spin flip. The spin system gives its excess potential energy to the lattice, essentially heating it up slightly.
And this energy is transferred as...
As phonons. Quantized packets of vibrational energy, like sound waves at the atomic scale.
And this spin-lattice relaxation, is that relevant to MRI?
Absolutely central to it. When those radio frequency pulses in the MRI machine excite the protons into the high-energy spin state...
How do they get back down?
They relax primarily through spin-lattice relaxation. They dump that extra potential energy into the surrounding tissue, the lattice, as heat, as phonons.
And the rate of this relaxation is important.
Critically important. It's called the T1 relaxation time. And it's different for different tissues, fat, water, muscle. That difference in relaxation time is what MRI machines detect and use to create the image contrast.
So let's summarize that contrast again. A slowing flywheel releases energy continuously,
while a relaxing spin system releases a single discrete packet, a quantum of potential energy, either as one photon or into the lattice vibrations via phonons.
And energy conservation is like a strict gatekeeper.
Absolutely. A spin can only flip if it finds a valid pathway that conserves energy exactly by coupling to another system that can provide or accept that precise quantum of energy.
Okay, this really changes the picture. So what does this all mean in practice, this understanding of spin? It's not just theory locked away, right?
Not at all. It underpins some of the most cutting-edge technologies we have. And importantly, these applications confirm that we treat spin as a stable, two-level information carrier, not a variable energy source. Well, if the flywheel analogy were right, these technologies would look completely different. They work because spin is a fixed property we can orient, not an energy tank we can drain.
Give us an example. What about spintronics?
Right, spintronics, revolutionary field. It uses the electron's spin in addition to its charge.
So regular electronics is just about charge current flow, zeros and ones, based on charge presence.
Exactly. Spintronics adds another layer, spin orientation. Spin up or spin down can also represent zeros and ones.
What kind of devices use this?
Things like the read heads in modern hard drives, giant magnetoresistance or GMR heads, also MRAM, magnetic random access memory. They work by detecting changes in electrical resistance depending on whether electron spins are aligned or anti-aligned.
And the goal isn't to get energy from the spin?
No, the goal is to flip the spin orientation using as little energy as possible to store or read information. The big hope for spintronics is actually much lower power consumption, precisely because you're manipulating a quantum state, not pushing lots of charge around.
Fascinating. Okay, what about quantum computing? Spin seems tailor-made for that.
It absolutely is. Those discrete spin-up and spin-down states of a spin-12 particle, that's a perfect physical realization of a qubit.
The quantum version of a classical bit.
Right, and unlike a classical bit that's 0 or 1, a qubit can be in a superposition, a combination of both spin-up and spin-down simultaneously.
And quantum computers manipulate this.
Exactly. Quantum algorithms manipulate the quantum information stored in these qubit states. Again, the focus is entirely on controlling and reading the state, the information, not extracting energy. In fact, a huge challenge is making the spin states stable for longer, increasing the coherence time so they don't lose their quantum information too quickly.
So stability, not energy storage. Makes sense. And then the big one, MRI. You explained its connection to relaxation, but let's just walk through how it uses spin as a probe, not a power source.
Sure, MRI is maybe the best example of using spin's interaction energy. It's not about the energy in the spin, but how spin responds to its environment.
So step one, you go into a strong magnet.
Right. That aligns a tiny fraction of the protons, the hydrogen nuclei, which are spin 12 in your body's water and fat molecules. A slight preference for alignment with the field.
Step two, the RF pulse.
Yep. A radio frequency pulse tuned precisely to the energy difference between the spin states in that magnetic field is sent in. This kicks some of those aligned protons into the higher energy anti-aligned state, resonant absorption.
They absorb the energy from the RF pulse.
Exactly. Then, step 3, the pulse turns off.
And the excited protons relax back down.
Correct. As they relax, primarily via that Spin-Lattice T1 relaxation we discussed, they release the potential energy they absorbed. They emit a faint RF signal of their own.
And the machine detects this signal. But how does that make an image?
This is the clever part. The rate at which they relax the T1 time is different depending on what kind of molecule the proton is in. Fat protons relax faster than water protons, for instance.
So different tissues give different signals.
Precisely. And by using additional magnetic field gradients, slightly varying the field strength across your body, the machine can pinpoint where the signals are coming from. It maps these different relaxation times and signal intensities to create a detailed picture of your internal tissues.
So it's all about using the spin's interaction with the magnetic field and its local molecular environment as a sensitive probe.
Couldn't have said it better myself. It's the quintessential example of leveraging spin's interaction energy and properties, not treating it like some tiny energy battery.
Wow. Okay, so wrapping this up for you. Our deep dive today really hammers home this fundamental disconnect, doesn't it, between our everyday classical intuition and the quantum world.
It really does. We've seen particle spin isn't an energy reservoir. Its magnitude is fixed. Intrinsic.
Right, unchangeable.
And the energy we associate with it, it's potential energy arising only from interaction, usually with magnetic fields.
And energy conservation is perfectly obeyed, but through these discrete quantum leaps, exchanging exact energy packets.
Photons or phonons, yes. Precise accounting.
You know, the fact that the early pioneers even used the word spin shows how hard it is to grasp these concepts. Our analogies just break down.
They do. They're useful starting points, perhaps, but you have to let them go to really understand the quantum reality. They become actively misleading if you cling to them too tightly at this scale.
So resolving this paradox isn't just a technical fix.
Not at all. It gives you a much deeper appreciation for how reality actually works at its most fundamental level. It's elegant, consistent, often deeply strange, but consistent.
And connecting it to the bigger picture, as you said. Thinking of spin as part of a particle's identity, not its motion.
It changes how you view everything. Structure of matter, why atoms behave the way they do, even fundamental rules like the Pauli exclusion principle, which dictates how electrons arrange themselves in atoms based on their spin states. It all ties back to spin being this fundamental intrinsic property.
A different way of seeing the building blocks of the universe.
Exactly. Not tiny tops, but fundamental quantum properties with profound consequences.
Absolutely fascinating. Well, thank you for guiding us through that. And thank you for joining us on this mind-expanding deep dive.
Keep questioning.
Keep questioning, keep exploring, and keep learning. We'll catch you next time.